So you are from?
I'm from Tamil Nadu.
Okay. You are
Yeah.
joining these classes or the first time? You joined last
No,
time?
no, already joined. Last time also I joined.
Okay. So what are you doing right now? MSc?
No, MSc completed. Now I'm doing job.
Okay. Where?
Hyderabad.
You want to pursue PhD by giving GATE?
Gate score I need for bar. Like that is some government sectors I need for that only.
Okay.
Huh. You are doing PhD, no?
Yeah, I am doing PhD from IISc Bangalore.
Okay. Bangalore?
Yeah.
Okay, okay.
Good evening, ma'am.
Good evening. So we will wait for 5 minutes and then we will start. Okay.
Yeah, okay.
guys can see my screen.
Yeah, yes, ma'am.
Yes, ma'am.
Okay, so we will start. Meanwhile, if someone joins. So, till last class, we were discussing about the questions which came in GATE 2021. So, from today, we will start discussing questions which came in GATE 2020 in organic part. Okay. So, okay. So, first today we will start with this question which came in GATE 2020. Question number 8. So, the question is the correct statement regarding the substitution of coordinated ligands in nickel tetracarbonyl and CO NOCO whole 3 is what? Like the options given are both nickel tetracarbonyl and the cobalt complex follows associative and dissociative pathways respectively. The second option is the nickel carbonyl complex follows a dissociative pathway, whereas the cobalt complex follows associative pathways. The third option is both nickel tetracarbonyl and cobalt complex follows associative pathway. And the last option, option number D, is both nickel tetracarbonyl complex and cobalt NOCO whole 3 complex follows dissociative pathway. So in this question, they have given that the cobalt nitrogen oxygen, this bond is nearly linear and the atomic number of cobalt is 27 and nickel is 28. So for this, first, like this is the ligand substitute. They are asking about how ligand substitution reactions will take place. So if you people remember, when we solved questions from GATE 2021 paper, there was also a ligand substitution reaction type of question. It was from base hydrolysis, and that was for octahedral complexes. But in this question, the given complexes are tetrahedral. So, for tetrahedral case, the ligand substitution reaction is of this type, where ML3X, where there ML3X means there will be three ligands of same type, and X can be equal to L, also not equal to L, and then one incoming ligand will come, and we will get the ligand substituted product ML3Y. So this ligand substitution reactions can take place by associative or dissociative pathway. So what is associative mechanism? When the reaction intermediate, in this case, for associative mechanism, this is the mechanism ML3X will react with Y to give Ml3XY, and then X will leave to give Ml3Y. So here we can see that first this incoming ligand is coordinating with the initial metal complex, and after that one ligand is removing, it is releasing to give the final ligand substituted product. Okay, so for associative mechanism case, this reaction intermediate has higher coordination number than the reactants and products. So in this case, what is the coordination number of the reactant ML3X? Anyone? Hello, am I audible? 4, yeah. So, and the reaction intermediate is having a coordination number of 5, right? Whereas the product also have a coordination number of 4. So for a complex to do substitution reaction via associative mechanism, the necessary conditions are that this metal complex should not be an 18 electron complex. Okay, so why? Because if it is already an 18 electron complex, then this complex will be electron rich, and also coordinatively, like if it is electron rich, then we know, as per the 18 electron rule, that complexes are more stable when they are in 18, when the total number of electron count, valence electron count, is 18 electrons, right? So they won't prefer to go to 20 electron system. Like they can come down to 16 electron, but it will get very crowded if it shifts to 20 electron system. That's why metal complexes in which there are already 18 electrons present, they don't generally prefer associative mechanism in tetrahedral complexes. Now moving on to the another method, which is dissociative mechanism. So in dissociative mechanism, we can see that here coordination number is 4, whereas the intermediate, the coordination number of is 3, and again in the product the coordination number of 4 is 4. So what happens in this reaction is that first we are having our initial complex Ml3X. It will first dissociate into Ml3 and X, and then this Ml3 will react with the incoming ligand Y to give Ml3Y, and this will be the substituted product, ligand substituted product. So for sorry, this is for your complexes. This dissociative mechanism we see for 18 electron complexes. So now moving on to the complexes which are given in the question. So what is the total valence electron count for nickel tetracarbonyl complex? Nickel is having how many electrons in its d orbital?
8
10.
electrons.
Okay. And CO, carbonyl, is how many electrons donor?
8. It
Yeah.
will donate total
So
8.
we have total 4 number of carbonyls, and each of them donate 2 electrons.
2 electrons.
So it will make a total of 18 electrons, right? Now moving on to the next complex, which is cobalt. So in cobalt, CO whole 3 NO. Total how many electrons? Cobalt is having how many electrons?
9.
9.
So 9. Each carbonyl group will give 2.
6
And
electrons.
now we have to think about this NO ligand. Okay. So anyone, how many electrons NO is donating here?
3.
Yeah, why 3? Because we can
It
see
is
that in the
bent.
question it was
Bent
given
electrons.
that the CO-NO bond is nearly linear. Okay, so there are two ways in which NO can coordinate. One is linear. If it is coordinating linearly, then it is a 3 electron donor. and the other way is bent. If it coordinates in bent fashion, then it is an one electron donor. Okay. So here, as in the question, it is given that in this complex, the bond between CON and O is nearly linear. That means here NO is a 3 electron donor. So the total electron count in this case is also 9 plus 6 plus 3, that is equal to 18, right? So from this, then we will think that both of them should go by dissociative mechanism. But this is not the case because, see, in this complex, in this nickel tetracarbonyl complex, what is happening is it is a complete 18 electron system, and for the reaction to take place by ligand substitution reaction, means this CO, 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 CO. So first, one CO have to leave. It will give Ni, CO, CO, and CO. Then an external ligand Y is coming, and we are getting NiCO, CO, CO, and L. Whereas, as we discussed, for the case of nitrosyl ligands, it has two ways in which
Excuse
it
me,
can
ma'am.
coordinate. Okay. So, if we are having any ligand like this, which can decrease their hapticity, okay. So, if that is the case, like for so what will happen is, now it is, since it is coordinating in a linear fashion, it is giving 3 electrons. But this thing like NO can coordinate in bent fashion to make a 16 electron complex, right? So what is happening is CO, 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 and one NO we are having, right? So this is an 18 electron complex. But from here, what will happen is it can become a 16 electron complex because NO can coordinate in bent fashion. So it will prefer to go from an 18 electron complex to an 16 electron. Sorry, this I joined in bent fashion. This should be like this. Okay. And in this case, it will be in bent fashion. So now this compound is having how many electrons? 9, 2, 2, 2, and 1, right? So it is a 16 electron complex. So if we have 16 electron complexes, then what happens is the external ligand first comes and it will give a coordination number of 5, and after that one of this ligand, CO ligand, will leave to give the final 4 coordinated product. So that means for the case of NiCO4, the reaction is going via dissociative mechanism, whereas for CO whole 3, NO, just because of the presence of this nitrosyl ligand, which can change its like from 3 electron donor to 1 electron donor, because of this, it is becoming 16 electron complex, and now this complex will, that's why prefer, like it will, the ligand substitution reaction will go via associative mechanism. So the correct option among these are, here what is the question, NiCO4 follow associative and this follows dissociative. No, this is not the correct option. Nickel tetracarbonyl follows dissociative and CO whole 3 follows associative pathway. So this is the correct option for this given question. Now any doubt?
मैम
Yeah.
लास्ट क्लास में आपने बताया था कि जब एनओ वेंट फैशन में अरेंज होगा तो थ्री थ्री इलेक्ट्रॉन डोनर और अगर लीनियर होगा तो वन इलेक्ट्रॉन डोनर.
No, no. It's the other way round. If NO, मतलब अगर NO is binding in linear fashion, then it is a 3-electron donor. Did I say this? Like, if it is linear, then it's 3-electron donor. This is the correct one. Okay. And if it is attaching in a bent fashion, then it is a 1-electron donor. This is for nitrosyl ligands. Hello.
Okay, ma'am.
Okay. And not only for nitrosyl ligands, all these ligands, like, suppose, let's say we have this ligand. Okay. So in this case, what can happen is we are having total 3 carbons here, right? So in these cases, what can happen is all the 3 can coordinate to a metal center. This is one case. So in this case, the ligand's hapticity is 3. Whereas it is also possible that the metal is only binding to this. So in this case, the hapticity will be 1. So whenever these kind of ligands are present, that means it is possible to reduce the total number of electron count. Then, like always, associative mechanism take place. Like, if this was the ligand present, then what will happen is from eta is equal to 3 to it will reduce its hapticity to 1, and it will become a 16 electron complex, and it will give the reaction in associative mechanism. So this is common for, you can say, all the ligands which can change their hapticity. Okay. Any questions?
No, ma'am.
Okay. And you can go to this NPTEL video on coordination chemistry, which is given by Professor Devashish Rai from Department of Chemistry, IIT Kharagpur. This is the link for the video. So there you can see whole lecture, complete lecture series on coordination chemistry. There you will also find the substitution kind of reactions. Okay. So can we move on to the next question? Okay. So this is the next question. Question number 10, which came in GATE 2020. So the question is, in oxyhemocyanin, the coordination number, mode of oxygen binding, color, and the net magnetic behavior of copper ions respectively are. So in this question, we are asked, like, first we have to say what is the coordination number of the of copper which is present in oxyhemocyanin. Then we have to find out the mode of oxygen binding. The next thing is the color of this complex and magnetic behavior. So what is hemocyanin? This is the structure of hemocyanin. So hemocyanin consists of 2 copper centers. Okay. When hemocyanin is not attached to oxygen, we are having copper in +1 oxidation state. So copper is in each of the copper is in +1 oxidation state, and each of them are coordinated to 3 nitrogen from 3 histidine residues. Okay. So this is the structure of hemocyanin. In hemocyanin, copper, we know that copper is a how many electron system? Copper is having how many electrons in its d orbital?
D10, ma'am.
No. Copper is actually
D9. Yes, ma'am.
D10s1.
Yes.
Okay. But since here copper is present in plus 1 oxidation state, that's why it is a D10 complex. And therefore, hemocyanin is colorless in nature. Okay. Hemocyanin don't have any color. But when oxygen binds to it, when this dioxygen is binding, then it binds in this fashion. So Cu, O, O, Cu. Right. Now that both the both the metal centers, they are going to plus 2 oxidation state. Okay. So in oxyhemocyanin, from hemocyanin to oxyhemocyanin, copper is becoming from copper plus 1 to copper plus 2. If it is copper plus 2, now it contains how many d electrons? D9, right? Okay. Am I audible? Hello?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So now copper is a D9 system. See, if in this case copper was D10 system, D10 means it is like all the d orbitals are completely occupied. Then there like no dd transition, nothing is possible. That's why we were seeing a colorless compound. But when it is becoming a D9 complex, then D transition can take place, as well as we discussed earlier also, that O2 minus kind of ligands, then so the oxygen, these ligands, what they can do is they can bind to like they can donate their electron to the metal center. Okay, since they are electron rich, whenever we have ligands like oxygen, cyanide, these type of ligands, they can donate their electron to the empty metal center, and therefore in this case also same thing, same kind of like process is happening, and from oxygen, it is donating electron to copper, and we can see ligand to metal charge transfer. Okay, and because of as ligand to metal charge transfer are both spin and Laporte allowed, that's why we observe intense colors for these complexes wherever ligand to metal charge transfer happens, and hence this compound is blue in color. Okay, so from this we got answer to like, yeah, also they have asked what is the coordination number in oxyhemocyanin. So what is the coordination number here for copper?
Five,
Hello?
ma'am.
Yeah. So we know that coordination number is 5 and the compound is blue. Okay. Also, we can see that here in oxyhemocyanin structure, it is mu eta 2 eta 2, like how oxygen is binding. Oxygen is binded to both the copper centers, right? So that means it is having an hapticity of 2. So that's why this mu eta 2 option is correct. So from this slide, what all we understood that mu eta 2 coordination number is 5 and the color is blue. Now, to know like what is the nature of O2 in this complex, we have this Raman stretching frequency. The Raman stretching frequency for oxyhemocyanin is around 750 centimeter inverse. This is the chart for various oxygen species and their stretching frequencies. Okay, so we can see that it is close to this 802. Therefore, like this is how researchers like confirm that in oxyhemocyanin, O2 2 minus is the nature of oxygen dioxygen which is coordinated to the two copper centers. Okay. So from here then we have our answer that the coordination number is 5. The mode of O2 is mu eta 2 and O2 minus the color is blue. Now the next thing is what is the magnetic behavior of oxyhemocyanin. So to know that, um, we know that it is having 9 electrons. So anyone, what should be the magnetic behavior of this complex?
Diamagnetic, ma'am.
Why diamagnetic?
Paramagnetic.
Yeah. And why paramagnetic?
Unpaired electron.
Okay. So from here, like here comes this fact of antiferromagnetic coupling. Okay. So what happens in this case is it is having unpaired electrons. So generally, if we see, like we will say that it should be paramagnetic complex. But here you can consider like this is one metal center, this is one copper, and this is another copper, and this is oxygen. Okay. So what is happening is like you say it has D9. D9 means one unpaired electron is there. So this one unpaired electron and it is bridged via an oxygen atom, right? So this oxygen is having spin paired electron, right? How to say? See, if this is the compound, okay. So it is having one unpaired electron, this metal center, and in oxygen we know that it it is paired electron. So one will be upspin, and the other will be downspin, right? And then this metal, again one unpaired electron should be there. But what happens is because of this, like because of this is bridged, this oxygen is bridged between the copper centers. Because of the presence of this unpaired electron in oxygen, because of the presence of this electron which is upspin, let's say it is upspin, if we consider this as downspin, then it is upspin. Okay, so because of the presence of this upspin electron in oxygen, it will polarize this and it will make this electron to go to downspin. Okay, so that this pairing can take place. So this type of coupling is known as antiferromagnetic coupling. This is called antiferromagnetic coupling. So here you can see, here there is paired spins of oxygen, and these are the first, there are both unpaired electrons. Then what happens is because of the presence of this bridged oxygen, it is becoming spin paired, and because of antiferromagnetic coupling is taking place, and now we don't have any unpaired electron. So the answer, like this complex, is diamagnetic, okay, and not paramagnetic. It is diamagnetic just because of the presence of this bridged oxygen, which induces this antiferromagnetic complex in this compound, and hence pairs up all the unpaired electron and the complex becomes diamagnetic. So the answer to our question is coordination number is 5. Coordination number is 5 in these two options. Then the mode is mu eta 2 O2 2 minus. Okay. So here these two things are matching. Then the color is blue and the magnetic behavior is diamagnetic. Okay. Is it clear?
Yes, ma'am.
Clear to all?
Yes,
Yes,
ma'am.
ma'am.
Okay. So for this, you can get basics in inorganic. You can go through the lecture series in basics in inorganic chemistry, which is delivered by Professor Devabrata Maiti. He is from IIT Bombay, Department of Chemistry, and Bioinorganic Chemistry series by Devashish Rai from Department of Chemistry, IIT Kharagpur. The links for these two lecture series are given here. Okay, so you can go through it for more and like to know more about this topic. Then we can go on to the next question. So the next question is question number 11. This question is also from inorganic chemistry. This like structure we have to say. The question is among the following species, the one that has pentagonal shape is. So we have to choose which among these four complexes, these four compounds given have pentagonal shape. So they have also given atomic numbers for all the atoms. Okay, so let's find out then. For XeOF4, XeOF4 is the first compound given. First, tell me what will be the hybridization of this compound. Anyone? Hello.
sp3d2.
Okay. So sp3d2 means which shape? Okay, I will do for this. So there is one way how I do. Like whenever first I count the total number of valence electrons. Then what I do is divide this whole thing by 40, like by 8. So it will come 8 5s are 40, and then whatever will be the remainder, if it is less than 8, I again divide it from 2 and we get the, so 5 plus 1 is 6, it is sp3d2. So this is how I calculate, like I find out the hybridizations. I'm sure you all are having your own ways, right? So for this complex, it is an sp3d2 complex. Okay. sp3d2 means if sp3d2 has zero number of lone pairs and six bond pairs, then the structure will be either square bipyramidal or octahedral. Okay, or octahedral if it has five, like all the bonds as bond pairs only, and there are no lone pairs present. But we can see that in here, xenon oxygen will make two bonds and F4, right? That means only five bond pairs are there. Now, if five bond pairs are there, that means it is, what is the shape of this compound then? Square pyramidal, right? Is it fine?
Yes, ma'am.
Yeah. So the next complex which is given is IF5. Similarly for IF5, iodine means 7, fluorine also has 7. So this is also same, है ना? It is also having 42 electrons. So in this case also it is sp3d2. Is everyone following?
Yes, ma'am.
Yeah. It is also sp3d2, but here also we can see that there will be 5 bonds only, right? Because 5 fluorine. So in this case also the shape will be square pyramidal. Fine. Now moving on to the next compound. What is the next compound? SF5 minus. So for SF5 minus, sulfur means 6, 5, 7 plus 1, 5, 6 plus 35 plus 1. So 36. This is also same, right? And in this complex as well, we are having one negative charge, but like it is not a bond pair, right? So here also the shape is not pentagonal, it is square pyramidal. Now another complex, it is H3F5 minus. Xenon is 8 and did I do anything? Oh, sorry. One more charge, electron will come for this negative charge. So it is 35 plus 8 plus 1, right? So it's 44. 44 means it's sp3d3, right? The hybridization is sp3d3. That means the structure of this complex is PBP. Discussed it in last class. PBP means pentagonal bipyramidal. So the shape will also be pentagonal bipyramidal if it has 7 bond pairs and 0 lone pairs. Okay. But here we can see that there are 5. Right? There are 5 bond pairs only. That means F, 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 and we have here will be 1 minus. So here we can see that there are 5 bond pairs. If there are 5 bond pairs, then we will get pentagonal as a shape. Okay. So see, pentagonal bipyramidal means what? There will be 5 ligands which will coordinate in this fashion, and one will be up, one will be down, because of which this bipyramidal name. But if we are not having these two bonds, then it will give us what shape? Pentagonal shape, right? So therefore, for this question, which is among the following species, the one that has pentagonal shape is HCF5 whole minus. Is it clear?
Yes, ma'am.
Yes, ma'am.
Clear to everyone, right?
Yes, ma'am.
Okay. So then we will move on to the next question. The next question in organic chemistry question is question number 18. Okay. So, excuse me. The question is the maximum number of microstates for P2 electronic configuration is. So, do you guys know how to find out microstates? Wait.
Yes, ma'am.
We have a formula actually. Okay. Like if you know that formula, you will get it very easily. So the formula for this number of microstates is equal to n factorial divided by r factorial into n factorial. Okay. So what is N? N is twice the number of orbitals. And what is R? The number of electrons in that orbitals. So in this case, it is asking for d orbital, right? For d2 it has asked. So d means we have how many d orbitals? 5, right? Which are mainly dxy, dyz, dxz, the x square minus y square and the z square. So we have total of 5d orbitals. Therefore, here n means 2 into 5, which is equal to 10. Is everyone following?
यस मैम मैम बट वहाँ पे n फैक्टोरियल अपॉन n फैक्टोरियल कैंसिल नहीं हो जाएगा नीचे शायद n
Sorry,
फैक्टोरियल
sorry, sorry. I am very sorry. It is n minus r factorial. Yeah. Thanks for pointing out.
45.
Hello?
यस मैम
Yeah. Yeah. And then R means total number of electrons. So here we have been asked for D2. That means here R is equal to 2. Right? So then we will put in this equation. So 10 into 9 into 8 factorial divided by 2 factorial into n minus r means 10 minus 2, which is equal to 8 factorial, right? So this is 10 into 9 into 8 factorial divided by 2 factorial into, just wait, somebody wants to join.
Factorial 8 में.
Yeah, someone was asking for joining. So 2 factorial and here 8 factorial. So this 8 factorial will get cancelled out, and 2 factorial means 2 only. So 2 5 are 10. Therefore, the answer will be 9 into 5, that is equal to 45. So the maximum number of microstates for D2 configuration is 45. Clear?
ठीक है मैम
Everybody followed?
Yes, ma'am.
Yes, ma'am.
Okay. And this is the next question. This is question number 34. Okay. So in this question, it's in the electronic absorption spectrum of an aqueous solution of nickel hexaammonia complex, okay, NiNS3 whole 6 2 plus, a very weak band is observed between the bands due to the transitions 3A2G to T2, 3T2G and 3A2G to 3T1GF. The transition responsible for the very weak band is. So these are the given options. In this question, we have been asked that the very weak band which appears between these two bands, okay, which is 3A2G to 3T2G and 3A2G to 3T1GF, like this corresponds to what? Okay, and for NiNS3 whole 6 2 plus. So first of all, nickel is how many electron complex?
D8.
Okay. So D8S2, it is 3D8 4S2. But since here nickel is present in +2 oxidation state, so D8. Okay. So for this question, we have to go, like, we should know the Tanabe-Sugano diagram. Okay. So nickel is mainly this, right? 1, 2, 3, 4, 5, 6, 7, 8. So these three transitions are like they are mainly the spin allowed transitions. Okay. So you see, first of all, in D8 complexes, we will have F as 3F as one term symbol, 1D, 3P, and then 1G and 1S. Okay. So term symbol, I think you people know term symbol. Hello. Hello.
Yes, ma'am.
Yeah. So like 3F is the ground state because what is happening is plus 2 plus 1 0 minus 1 and minus 2. Here we have 1 2 3 4 5 6 7 8. So L is equal to summation of ml, which is 2 plus 1 here 3, and 3 corresponds to F. So this is F will have F, like the ground state will be F. And why this 3 came? That is because there are total 2 unpaired electrons. So each electron is having half as spin multiplicity. So half plus half, which is equal to 1, and spin multiplicity means 2s plus 1. S is half plus half 1. So here 2s plus 1 means 2 into 1 plus 1, which is 3. So here that's why for D8 case 3f is the ground state term symbol. Okay. So one is 3f and then 1d, 3p, 1g and 1s. These are the states. And the possible transitions which takes place in D8 complexes, like possible, no, it's not possible. The spin allowed transitions. Okay. So we know these rules, right? Spin allowed means transitions are spin allowed only when, while after the transition, the change in spin multiplicity should remain 0, right? Then only that particular transition is called spin allowed. So the spin allowed transition for D8 case are 3A to G to 3T to G, okay? Then 3A to G to 3T1G and 3A to G to 3T1. Okay, so this 3T1G is coming from the F term, whereas this T1G, 3T1G is coming from the P term. So this is another possible spin allowed transition. So anything which is apart from, like, which is not a spin allowed transition, we observe weak bands for those transitions. Okay. So in this question, there are no options given which has same like transitions which are spin allowed. But if you get any question in which you can see like options where where there will be few options which are spin allowed and which will be spin forbidden. So in that case, you should always know that the spin forbidden transitions gives weak band. Okay. Now coming on to this question again. So in this question, what they are asking is between 3A to G to 3T to G and 3A to G to 3T1G F. That means they are talking about this transition, right? This band and this one. 3A to G to 3T to G and 3A to G to 3T1G F. So here we can see the options given are 3A to G to 1T1G. Can we see anything here like in between these two transitions there is no 1T1G and like 1T1G, right? Also we can't see any state with state 1 T2G. Yeah, 1 T2G is there, but it is very high in energy. It generates from 1G term symbol, and the energy for this will be this transition. So it will nowhere lie between the transitions from 3A to G to 3T1GF, like between these two transitions. So this is not the correct answer. This 1T1G, this is also not the correct answer, as this is also lying. You can see from it is generating also from 1G, and it is lying above these two transitions. So this will also not be the option. Then 3A2G to 1 even G. Where is 1 even G? So this is 1 even G. Yeah. So 1 even G is lying between these two transitions. Okay. So this can be correct. And the next option given is 3A2G to 1A2G. Okay. So we can't see any. Can you see anything as 1A2G? No, right? So this is not the option. So for this question, the transition for which we are observing the weakest band between the transitions 3A to G and 3A to G to 3T to G and 3A to G to 3T1GF is 3A to G to 3 1 to 1EG. Okay, so this is the weakest band. This is the weakest band between these two given transitions. Okay, hello.
Yes, ma'am.
Okay, so one thing is that generally, like this type of this was the question in which we have to somewhat you can say that remember this Tanabe-Sugano diagram. So generally these questions don't come. Mostly it will come from Orgel diagram and all. What I said, like spin allowed, spin forbidden. On that basis they can ask you. But this was a bit rare example where I saw that we have to know this Tanabe-Sugano diagram. So mostly this don't come, but if it comes, then you have to do such type of questions via Tanabe-Sugano diagram. Okay, is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So today we will like up to this question only. You have any doubts from all the questions, like all the 5 questions which we solved, you can ask me, or anything apart from that which you have doubt from previous class or something, you can ask. So you people are also watching the lecture series which are given in NPTEL, like on different topics. Hello? Okay. No, I was asking about the like chapter courses, like as I said for bioinorganic chemistry and all those things. So if you want any like further details for this topic, you guys can go through that. And if you are facing any problem, you can ask. No problem with that. Okay. So we will
Okay,
be
ma'am.
solving this GATE 2020 chemistry questions. So you guys can go through that question paper and come. So it will be easier for you people as well as for me because you will be able to follow it more properly.
Sure,
Any
ma'am.
feedbacks about this class? Anything which you want me to do, like any change or anything?
All good, ma'am.
Okay. Okay then. Again, if you have any doubts, you can always reach me through this mail ID. I'm sharing @gmail.com. Okay, I have shared it in chat box. If you people have any problem, you can contact. And also the like whatever I am solving here for each and every like different question, you will find like solved video solutions that also you can go to the gate portal and you can get that. Whatever we are doing now, it will take a little bit time to get uploaded, but the previous year ones you will get it soon, I hope. Okay, then we will end the class. Any questions, anyone? Okay, then. Thank you, everyone.
Thank you.